Okay, welcome back to physics. We are going to spend the next several lessons trying to do something which is a little more challenging. We're going to try to determine the electric fields that are created by objects that have charge spread out over them. And this is a little more challenging. So in other words, the charges aren't all in a point. They're not all a ball of charge, but they're spread out. Like maybe they're spread out on a sheet or a line or a ring. And we're going to have to use calculus to figure out what the electric field looks like around those objects. So the first example that we're going to do is the simplest one to do with calculus, and it's going to be a ring of charge. So I'm going to read the goal here, and feel free to just take notes directly into this, into your packet. The goal is going to be to derive an expression for the net electric field at a point P along the line of symmetry passing through a uniformly charged ring of radius A and total charge Q. Okay, so that would be the task. Now, the ring itself, of course, this is the ring, obviously. And the assumption that we're going to make is that the charge is uniformly distributed around the ring. So why don't we assume that it's positive charge? So I could draw little pluses. And that kind of shows that you've got the charges are spread out. Now the ring itself, it might be a conductor. And when you put positive charge on the conductor, the charge is going to spread out evenly. Okay. It could also be an insulator, and it might be like a ring of plastic or something like that, and you give it a charge by rubbing it with something. So it doesn't really matter for this problem. What matters is that the charge itself is spread out evenly, so the charges are not all grouped in one place. Okay, now let's look at some of the things which are sketched in our diagram here. The radius of the ring is A. Okay, so this is the center of the ring, and the radius goes from the center to the edge. We're also going to be looking at electric fields along the axis of the ring. So our goal is going to be to find the electric field along this axis. And we're not going to go and look at points which are off of the axis, because it gets very complicated. So we have a pretty limited goal here, and we're just going to try to figure out what happens to the electric field as you go out this way. Probably, before we get into the math, you could think about this, and you could say, well, I would expect the electric field to be very strong if I'm close, and it should get weaker as you get farther away. And that would be pretty reasonable. So hopefully our answer will show that too. All right, other things which are on this figure would be the dimension x. X is the distance from the center of the ring to the point of interest, which is P. So x is a variable, and we are going to really be trying to find a function for the electric field as a function of that position x. So we can let x run from 0 all the way out to infinity, and we should be able to calculate the electric field. Okay, so other things we have here. The point P is shown. The angle theta is the angle that is made between this line, which goes from the edge of the ring out to point P. So we've got ourselves a nice right triangle inside here. A side A, a side X, a hypotenuse R. And let's get going with this. The way that we're going to handle this is that we're going to look at this ring, and we're going to divide it into chunks, into small pieces. And so a chunk is right here. We're going to say that that corresponds to a chunk of charge called dq. Okay, so it's a very small piece of charge. The entire ring, it has a charge, we'll say, of q total. Right, that's your total charge. But this piece here is only a small piece of it, right? And so to add up to that total, you'd have to kind of add up all those dq's. And all the dq's, if you went all the way around the ring, would add up to q total. I'll just put that in parentheses just so that you can see that. But that's the relationship between those. Okay. All right, so what we're going to do is we're going to focus in on this dq, which is at the top of the ring. And that dq is going to create an electric field. which is directed along this R direction, and it's going to be kind of diagonal down here. And that's going to be called dE. Okay, so dQ is producing an electric field at that point that we're going to call dE. And that dE has components. It has an X component which goes to the right. It has a Y component which goes straight down if we're looking at the dQ, which is at the top of the ring. So what we're going to do next is we're going to write an expression for the electric field at point P. And that electric field is going to be expressed in unit vector notation like so. There's going to be an X component to that field, and we might have a Y component. So we're going to write this with the I hat and the J hat unit vectors. Okay. Now, the thing is, though, is that this EX is not the same thing as that DEX, right? It's not. Because this EX is the total EX that comes from all of the chunks. The same thing here. This EY that's right here is not the same thing as DEY. Okay? And so what we'll have to do is to integrate to find those things. So what we're going to do is we're going to say that we're going to have to find the total EX by adding up all of the X contributions, all of the DEXs that are here, that come from all of the different chunks on the ring. So every chunk on the ring produces its own vector, DEX, and we would have to add those up by calculus, by an integral, to find out the total. We would also do the same thing here for EYs. We would add up all of the DEYs, okay, to find that. So this is the DEY. This DEY just comes from that piece. Now we're going to play a little trick here, and we're going to say that this integral, when you add up all those pieces, is actually equal to 0. So the total EY of the electric field here is 0. And the reason we can say that is because you can probably imagine that if I chose a chunk that was down here at the bottom of the ring, the chunk at the bottom of the ring would actually make a vector where the dy component, the DEY, goes up, and it would cancel the DEY component down here. So for every chunk that produces a DEY, there's going to be another chunk on the opposite side of the ring that cancels it. And so what we do is we just kind of say that the EY total is 0, and we say that's by symmetry. Okay? And what that means is that, again, for every chunk that produces a DEY, there's going to be a chunk on the opposite side of ring that cancels it. And literally, you just look at the picture to say that. And that's what we're done with that part. So this is going to be 0. Okay, sorry, I lost the line there. So this is by symmetry, and that's going to be 0. Okay, so now let's do the DEX integral. Give myself some space here. And so EX is equal to the integral of DEX, but if we look at the picture up here, DEX is actually going to be given by cosine of the angle theta. Okay, so you can look up here and you've got this right triangle right there. The angle theta on this side is also equal to the angle theta here. And if you make DE your diagonal, then the adjacent side is going to be your DEX. So we're going to replace DEX with DE times the cos theta, the hypotenuse times the cosine. So all of these DEs are just sides of a triangle, right? What's nice about doing that is then we can say that we can replace DE with Coulomb's law, or the field from a DE, which is K dQ over R squared. So the DE, right, again, the DE that comes right here, this vector, this diagonal vector, you could calculate the size of that if you knew the amount of charge that was sitting up here as your dq. And you would use the point charge formula to find that. So why did I write k dq over r squared? Because the field from a point charge is kq over r squared. And here we're calling q the dq. Okay, so that's how we substitute there. This is an important substitution that will come up in other places. You take a small chunk of charge, you treat it like a point charge, and then you can substitute like that. For the cos theta, we're also going to do a substitution because we don't want to have a theta in the integral because that's kind of awkward. We have a dq, we don't want to have a theta. And again, I'm going to look at the triangle, and I'm just going to recognize that in my triangle, actually, not that one, but let's look at the big triangle. If I look at this triangle, the cosine of theta, cosine is adjacent over hypotenuse, right? So if this is my theta, and I say the adjacent is x and the hypotenuse is r, I can do a substitution down here, and I can say that this is x over r. So cos theta becomes that. And that also is a substitution that we will do sometimes in some of our problems. So you can take a trig function and replace it with the dimensions of a triangle. All right, so the rest of this is actually pretty easy from a calculus point of view. A lot of stuff is going to come out here. In fact, pretty much everything is going to come out except for the dq. So we're going to be left with k times x over r cubed, and I'm going to just immediately bring that out of the integral because none of those things are going to really be changing with the dq. Okay. So in other words, as I go around the ring and I add up all of the different dq's, I'm never changing the x position. I'm never changing the r distance. So there's no reason for me to include those things in the integral because they're constants. So that's why I can bring x and r cubed out. When I complete this, the integral of dq is just going to be q total. So this is going to give me k times x times q, right? And q is the total charge on the ring. That's the total charge now. So that integral gives us that. And if we put this back into terms of the original parameters in the problem, we would write k times x times q. And my r is going to be a squared plus x squared to the 1/2. Whoops. To the 1/2. Right? That's what r is. But then I have to cube it. So this becomes kx q over a squared plus x squared to the 3/2 power. And that is that's the expression that we wanted. That tells us something about the x field as the field strength as you go along the x direction on the axis. Okay. So our final answer here would be, I suppose you could rewrite this and you could say, well, we've just figured out this function. We know now that that function is given by this. And so we have our solution. Just do a quick reality check on this. Remember, we said that as you go out further and further and x gets bigger and bigger, you expect the electric field to get smaller. So we would expect the electric field to be really big here and then get smaller, smaller, and really small as you go further and further out. So the electric field should get smaller.